I'm Munchi Maxwell, and this is a short video on engineering hacks. Our tutor for today will be Master Joseph Forte. Stay tuned and enjoy. Thank you.
Come to eigenspace. Here, possible questions are you might be asked to find the characteristic equation for the eigenspace. And then after finding the characteristic equation, you ask to find the solutions of the characteristic equation, and that would be your eigenvalue. And then, in the eigenspace, we have the equation is describing the eigenspace. Then in the eigenspace, we have eigenvalues with their corresponding eigenvectors. Okay, and so the next thing is the eigenvectors that is associated with each of the eigenvalues. So we know that in the eigenspace, we have the matrix being we have the matrix, and then we have a matrix of the eigenvalues, and then the determinant of that matrix formed by subtracting the matrix of the eigenvalue from the original matrix should be 0. Meaning that this matrix, the determinant of this matrix is 0, meaning this matrix is a singular matrix. So we are supposed to form a singular matrix by subtracting this matrix from the original one. And this matrix is formed by multiplying the eigenvalues by the identity matrix. Okay, so let's find, this is our matrix A. Okay, so let's find this matrix. So it's going to be this, and then this is the unit vector in this matrix space, and this matrix space is a 2 by 2 matrix. So we are going to get this matrix to be 3 minus our eigenvalue, then minus 2, then we have 1 here, then we have minus our eigenvalue. Like this. So this is our singular matrix, and the determinant of this singular matrix should be equal to 0. So let's find the determinant. And then finding the determinant, we are going to get like this is the determinant. So we know we have to multiply this diagonal by this diagonal. So that is going to give us 3 minus lambda multiplied by minus lambda, then subtracted from this diagonal multiplied by this diagonal. So that gives us this, and then it should be equal to 0. Okay, so in that case, we are going to have this to be minus 3 lambda plus lambda squared plus to be equal to 0, and so we get our characteristic equation to be lambda squared minus 3 lambda plus 2 equals 0. So this is the characteristic equation. This is lambda, and this equation is what is describing our eigenspace. Okay, and so the next thing is finding our eigenvalues. The eigenvalues are what gives us the eigenvectors. Okay, and then when you have an equation like this, I'm going to teach you a simple way of getting your eigenvalues. When your matrix is in the R2, that is in the 2-dimensional space, you don't need to and you don't need to go through a complex process to solve your equation. You can solve it with calculator or whatsoever it is. But when you have it like this, you just look for 2 factors of the constant C, and the constant here is 2. So the 2 factors that can span the coefficients of your lambda. So -1 and -2 will span our lambda. And then you just multiply each one by -1, and that gives you your eigenvalue. So therefore, our eigenvalue 1 is equal to 1, and our eigenvalue 2 is equal to 2. Okay, yes, so this is these are our eigenvalues. Now let's move on to find the eigenvectors associated with each of the eigenvalues. So for lambda 1 being equal to 1, this is how we are going to get. Now we know that this singular matrix formed by the eigenvalue 1 multiplied by our eigenvector should be equal to 0, giving us a 0 vector. Okay, so that is what we are supposed to do now. We are supposed to find this one, and then we find an eigenvector from this situation. So we know this one here, we had 3 minus 1, and then we had minus 2, and then here we have 1 and then minus 1. Where this 1 is our eigenvalue, just go straight to that, and that will give you, these are the entries of your eigenvector. This is the 0 vector. So we get 2 minus 2, then 1 minus 1, then entries of our eigenvector like that. There is no need of forming any augmented matrix here, because after multiplying through by your things, you are going to get, you can see that these two are linear. 1 minus 2x2 being equal to 0. So it's simple as that, as x1 equals x2. Okay, so we can just form our eigenvector for the lambda 1, and that is going to give us either x1, which is the same as x2. So if we take either this one or that one, we are going to get our eigenvector to be x1 out 1, 1. Therefore, our eigenvector for the lambda 1 is this, having entries 1 and 1. Now let's take our lambda 2. Our lambda 2 is equal to 2. So the same analogy, we try to find this one. This is our eigenvector for the lambda 2 and should give us this 0 vector. So we just subtract this from that, and that will give us 3 minus 2. This gives us 3 minus 2, and then minus 2, then 1 minus 2. Okay. Then we have x1 and x2 for the eigenvector 2, giving us the 0 vector. In that case, we are supposed to get 1 minus 2, then 1 minus 2, right? Then x1, x2 being equal to 0, 0. So we know that these are also linearly dependent. So we just take only one, multiply this by only one row, giving us x1 minus x2 equals 0. Okay. So we can say that x1 is equal to 2x2, right? So we can make x2 as free variable, or we can just deal with it like that, so that we represent x2 to be equal to t. Okay, so we know that x1 is equal to 2t, s2 equals t. So our eigenvector 2 is this 2t and then t. Factorizing t out gives us 2, 1. So we get our eigenvector 2 to be this 2, 1. Okay, so this, we have gotten all the things that describe that eigenspace.